Talking about continuity and whether or not a function is continuous at a particular point is important in calculus. Now, if I look at a simple graph like the one on the left, I'm pretty confident that is continuous. That is, I could draw that without picking up my pencil. The graph on the right-hand side, however, that's a piecewise function, and I could pretty confidently say that is not continuous at certain points because I'd have to lift up my pencil in order to draw it. But if I just stopped at, hey, no holes or breaks, then it's continuous. That's not going to help us with a picture like I have right here. This is a function f of x equals x sine 1 over x when x doesn't equal 0 and 0 when it does. Looking at that, it looks like it might be a piecewise function since I have a different value at 0. But is it? Can I draw that without picking up my pencil? I can't really tell looking at this graph. So we're going to come up with a formal definition of what it means to be continuous at a point. And here's my more formal definition. A function f is continuous at a particular point a if the limit as x approaches a of f of x equals f of a. That means it's the same whether I plug in a into the function or if I look at the limit. Otherwise, a is a point of discontinuity. We can use the following checklist to see if a function is continuous at a point. First, make sure f of a is defined. That is, a is in the domain of the function f. Make sure the limit as x approaches a of f of x also exists. The final step is to make sure those two numbers equal each other. This leads to a really important practical point. If I know a function is continuous, then in order to find that limit, instead of doing all the things we've been doing so far, all I have to do is plug in the value of a for x, and I get the limit. Direct substitution. So it's very useful to know whether or not a function is continuous at a particular point. Let's look at an example. So here's a graph. I think we looked at this in an earlier video. There looks like there's possible points of discontinuity at -2, 0, 2, and at 4. Let's first look at -2. All right, at x equals -2, f of a is in fact defined. It's equal to 4. The limit as x approaches a of f of x is also defined. That, however, doesn't equal 4. That limit as x approaches -2 from either side is 0. Therefore, even though it passes the first two items of my checklist, because f of a does not equal the limit of f of x as x approaches a, that means this is discontinuous. Let's look at our next example. At x equals 0, f of a does exist. It equals the number 0. However, the limit of f of x as x approaches 0, I'm not sure that exists. That's because the limit as f approaches 0 from the left-hand side is equal to 4, and the limit as x approaches 0 from the right-hand side of f of x is equal to 2. Since those two values are not the same number, that means the limit at that point does not exist.
Next, look at x equals 2.
That will be discontinuous for the exact same reason that it was discontinuous at 0. That is, the limit as x approaches 2 does not exist for f of x because the limit from the left and the right are not the same number. However, the last point, x equals 4, that is a continuous function. F of 4 looks like it equals 0, and the limit as x approaches 4 from either side is also 0. So the point at 4 is continuous. If we had a graph similar to this, that is when I have a vertical asymptote somewhere, the limit as x approaches 0 of this function is infinity. But even though we say it is infinity, we do understand that in actuality it does not exist. This infinity is telling us it gets to an arbitrarily large number, but because that limit does not exist, it is discontinuous at the point x equals 0. What about a function like this, where I have f of x equals x squared minus 1 over x minus 1? Looking at the graph, it certainly looks like it's continuous. My only worry is what happens at the point x equals 1. That point right there. I'm pretty confident that although the limit exists at that point, f of 1 does not exist. So, although we can factor and divide out that x minus 1, you need to know that at the point x equals 1, it is not continuous. Even though the graph in your calculator or Desmos would show it as a straight line, if you hovered over that point in Desmos, it would say that it was undefined at that point. The table function in the calculator would tell you the same thing. Now at x equals 2, we're fine. So this function is in fact continuous at x equals 2 because the limit does exist. It happens to be equal to 3, and that's the same thing as f of 2. All right, what about this crazy function I started off with? The question is, at 0, is this continuous? Well, my first check in my continuity checklist is fine. F of 0 is in fact 0 because of this second line of my function definition. However, what is the limit as x approaches 0 of x sine 1 over x? I'm going to have to use the squeeze theorem again. So the squeeze theorem, I need to find a lower point and an upper point that's surrounding or sandwiching my function. Well, let's first start off with sine of 1 over x. I know that goes between -1 and 1. What if I multiply all three parts of that inequality by x? Well, if I do that, I get this. Negative x is less than or equal to x sine 1 over x, which is less than or equal to x. If I now find the limits of the upper and lower limits of this, I find that by direct substitution, because these are polynomials, that the left-hand limit and the right-hand limit are both equal to 0. Therefore, by the squeeze theorem, the limit of x sine 1 over x as x approaches 0 is in fact 0, which means it is continuous. I'm going to come up with some rules about functions in general. First of all, I'm going to say that f and g are both continuous at a, c is a constant, and n is greater than 0 and is an integer. If I can say that, then I can also say the following. If I know that f and g are both continuous at a, then adding them together or subtracting them, those are also going to be continuous functions. So f plus g will be continuous and f minus g will be continuous. I can multiply f by a constant c, and that will still be continuous. And I can even multiply f and g together, and the result will still be continuous. I can divide f by g. As long as g does not equal 0, then this is also continuous. And finally, if I take f of x to the nth power, that resulting function will also be continuous. I can also talk about rules with polynomial and rational functions. All polynomials are continuous for all of x. That's pretty powerful. I can also say that rational functions, which are defined as a polynomial over a different polynomial, those are also continuous for all x as long as g of x is not equal to 0. So if I got a question like this, when is x squared plus 32x plus 1 divided by x squared minus 1 continuous? The numerator does not matter. One of my favorite things to do on tests is to do an absolutely crazy numerator, and then students they say, I've never seen anything like this before, I don't know what to do with it. The trick is you don't care about the numerator. The only thing you worry about is when g of x is equal to 0. Since I can factor x squared minus 1 into x plus 1, x minus 1, that means this function is continuous everywhere except when x equals 1 and x equals -1. Now we're going to talk about composite functions. If I have a function g, and it is continuous at a point A, and if f is continuous at, not that point A necessarily, but the point g of A, then f composed of g, or f of g of x, is also continuous at A. Let's look at an example of why we'd want to use this. If I had this, all I have to do is break this up into two separate functions. I'm going to think of f of x as being the outside function, that is x to the 10th power. G of x, however, will be the inside bit. So I don't have a rule that I could have used for this entire function. But if I know that I can use this composite rule, then I can look at these pieces independently. My g of x, that's simply a polynomial over a polynomial or a rational function. I can use direct substitution into this. So if I'm looking at when x approaches 0, g of 0 is simply equal to 12 over 6, or the number 2. Now all I have to do is determine if f of x is continuous at 2, and it certainly looks like that. So now I know that f of 2 is 2 to the 10, or 1024. We can expand this a little bit to another theorem. If g is continuous a and f is continuous on g of a, then the limit of x approaching a of f of g of x is simply equal to f of that limit of x approaching a of g of x. Number 2 looks awfully similar, but I have not said that g is continuous. I merely say that the limit of g of x as x approaches a is L. So that's a little bit less strenuous of a requirement than saying that G is continuous, because remember, continuity implies not only does this limit exist, but it also happens to equal what happens when I plug A into my G of X. The next thing we have to consider is continuity on an interval. If I have the following two graphs, I could say that both of these are continuous if I'm careful about my interval notation. Using interval notation, brackets mean the endpoint is included, parentheses means it is not. It gets infinitely close, but does not include that point. A little bit of more terminology. A function is considered right continuous at a point A if the limit as x approaches A from the positive side of f of x equals f of A. So this example at point A, that is right continuous, because as we approach that point A from the right-hand side, f of A equals that limit. The one on the right-hand side, let's look at point B. The graph on the right, if I'm looking at point B, that is left continuous because the limit as x approaches B from the left-hand side of f of x is equal to f of B. And I can talk about a function being continuous on an interval instead of just a point, if it's continuous on all the points on that interval I. You'll see some questions such as, for which values of x are the following continuous? This deals with root of functions. The example on the left is the square root. That is an even denominator. In that case, we have to make sure that what goes into my square root is positive. That means 9 minus x squared has to be greater than or equal to 0, which means 9 has to be greater than or equal to x squared. Well, I think that means that x has to be between -3 and +3. So I can say that this is continuous on bracket -3, comma, 3, end bracket. And I'm using brackets because underneath the square root, it can actually equal 0. So those endpoints are included. The second example, instead of an even number in the denominator of the exponent, it's an odd number. That means there is no limitation because I can take the cubed root of a negative number. And in this case, I can just say it's continuous for all x. We can also say that an inverse function is also continuous on I if its parent function is continuous on I. We do have to watch out for what the interval is, because the inverse function might have a different interval, but it would be continuous on the f of x as long as x was in that interval.